Welcome to the next module. In this module, we will be looking at Arctic amplification. So what is Arctic amplification? The temperature variability and the trends in the Arctic region tend to be larger than the trends and variability for the northern hemisphere or the globe as a whole. And this variation, the variability in the trend is called as the Arctic amplification. Traditionally, this is measured as the change in surface air temperature. The radiative forces, mainly from the greenhouse gas emissions, lead to the increase in the global surface temperature. Arctic surface temperatures increased 1.2 degree per decade. This is twice the global surface temperature increase. And a decrease in the surface albedo, that means a decrease in the sea ice concentration, their extent over the ice covered ocean, leads to global warming and Arctic amplified warming. So this is what we had seen in the albedo effect in the previous couple of modules. So there we had seen the solar radiation hitting the ice leads to more melting of the ice, and that leads to increase of surface temperature. So that is what we are actually seeing here as the Arctic amplification. The Arctic amplification influences both weather and climate at the mid-low latitudes, such as the occurrence of extremely cold events, heat waves, variation in westerly jets, and summer precipitation. So this is the major effect of Arctic amplification. And here is the observations what many scientists had made. Over the 43 years, the Arctic amplification ratio in observations and climate models are shown here. So for a shorter time period for which the Arctic amplification is calculated, the internal variability plays a larger role. And here you see this is the red one is the actual observation, and the black one is the theoretically calculated modeled one. So there are different models that are used: CMIP5, CMIP6, MPIGE and CANESM5. So if you look at all the cases, the red line is the observation, which is much higher than the models which actually predict. The black one is predicted by the model. So this is what we say as the Arctic amplification. So, and in fact, if you look at this, happened somewhere around 2010 or so. See, the calculation shown here are from 2000 and up to 2020. Then here there is also prediction for the future. So based on all these things, it was observed that there is a invariably higher temperature observed in the Arctic region, and this higher temperature is called as the Arctic amplification. So how does the Arctic amplification occur? So the concentration of CO2 in the atmosphere could alter the Earth's surface temperature, and that the temperature change would be especially larger in the polar latitude. This was given by Arrhenius in 1896. So this is the beginning of the information telling that Arctic may experience little bit higher temperature compared to the rest of the world. And then the initial warming will melt some of the Arctic's high albedo snow and ice cover. So that means the warming will lead to melting of ice. That is as simple as that. So this leads to a positive feedback, melting of ice leading to a vicious cycle. So that is how the entire cycle leads to more and more ice melting. The expansion or retreat of Arctic sea ice cover, altering the vertical heat flux between the Arctic Ocean and the overlying atmosphere. So this also happens. The changes in the atmospheric and oceanic heat flux convergence also forms. These changes in the cloud cover and the water vapor contents. So this affects the downward long wave radiation flux and soot on snow and heat absorbing black carbon aerosols in the atmosphere. So all these factors are responsible for the Arctic amplification. So when we ask the question why or how that Arctic amplification occurs, these are all the various reasons by which the Arctic amplification occurs. And we can say the amplification is basically, the initiation is based from the atmospheric dynamics that initiates the process, and this leads to the propagation. That means local physical processes and feedback. So the overall atmospheric change, that means globally the change takes place, and that leads to local physical process and feedback. So that is how the amplification actually progresses. So here the meridional atmospheric transport leads to the sea ice variability, because the wind direction changes, and this actually increases the moist static energy in the Arctic troposphere. So that leads to increase of temperature. And then when we see as the overall sea ice extent change, so the sea ice extent, let us say there is X amount of sea ice that is present, and now the atmosphere is warming due to this meridional atmospheric transport. So this leads to the increase in the moist static energy in the Arctic troposphere, that leads to little bit of atmospheric warming. So in the beginning, this will have little or no change, at least in the beginning. But over the years, what happens is the thinning and the reduction in the multi-year ice happens. So that is how the slowly, see, this is not just a 1 year or 2 year even. This is actually happening over a period of decades. And the thinning of reduction in the ice leads to open surface water. So as we have seen, surface albedo changes when ice melts to water. Now the water absorbs more heat, so it leads to more melting of ice. So that is what it is happening. So the thinning of ice leads to more and more open surface waters, which increases the summer heat accumulation. Now when there is more water, the albedo is very less. In other words, all the sunlight that is received by the Arctic water is being absorbed, so it starts to heat up. So that leads to the Arctic amplification. And here is the temporal coverage for essential climate variables collected in the ESA Climate Change Initiative. So this data is compiled from 1980 to 2020. So if you see here from 2000 to 2010, this is where the Arctic sea ice transition actually started happening. So this particular area is the time at which the Arctic melting started increasing. In other words, from 2010 onwards, we are seeing Arctic amplification at a larger scale. So here are some of the equations to calculate the change in the Arctic amplification is given by the Arctic temperature minus the total temperature of the earth. So from that we can actually see the difference in the Arctic amplification. So here RAA is the air atmospheric change in the Arctic region. So from this we can actually calculate how much is the Arctic region is getting heated up. So that we can actually see. There are various Earth observation missions which are happening in collaboration with the ESA. So first one is scientifically we do carry out a lot of experiments, and Copernicus is another satellite which actually gives lots of information, and the meteorology data is being captured. How do we carry out this study is basically the essential satellite observations are done. First we measure the sea ice, then the surface temperature, then the land cover, then altimetry and geomorphology, then ecological indicators and ocean color and soil moisture. So all these things are observed, and then the Arctic amplification is caused by the global warming. So this is our result, inference from these observations, and it is driven by the meridional heat inflow, and it is enhanced by the sea ice retreat, clouds and the surface layer feedbacks. So the sea ice retreat actually leads to more exposure of ocean water. So that ocean water leads to more absorption of sunlight, which leads to increase of temperature. So that is how the Arctic amplification happens. So here is the 5 events that are shown. The first one is the heat influx into the Arctic enhanced by the destructed polar vortex. So this leads to more and more surface air reaching there, and also the solar radiation reaching the Arctic region. So this leads to the disappearance of multi-year ice, and these are all the areas where the extreme Arctic amplification has been observed. The areas marked as 3 are the place where maximum Arctic amplification has been seen, and these areas are the place where the snow water started increasing. That means the whatever is the permafrost in these areas started melting, and here is the place where the areas of extreme heat waves is observed in 2020, and also in this area the Norslik catastrophe, that is oil tanker accident, happened in this particular area. So by monitoring this dynamic process, physical feedback and environmental impact related to the emergence of apparent amplification can be seen through these kind of images. And how the mechanism actually happens. So here we are going to look at the ocean heat transport. So how the ocean heat transport leads to Arctic amplification. So that's what we are going to see. So in the northern hemisphere, there is a positive OHT anomalies primarily result in the increased ocean heat convergence along the Atlantic sea edge where most of the ice loss occurs. So this is our, let us assume this is the entire Arctic region, and there is plenty of sea ice here, and Atlantic Ocean is in this side. So from the Antarctic to sea ice happens here as directly if we talk about the southern pole, but in the case of Arctic, so the ocean heat transport increases from the Arctic, then this leads to, this is the area where the sea ice and the water actually meets. So this area is where the actual heat transport convergence takes place. So from through this area, the heat reaches the atmosphere. So this is how the melting of ice. So the more and more heat transport happens leads to more and more disappearance or melting of that ice, so that this keeps on moving. In other words, the sea ice amount, that is the ice edge of this sea ice started reducing or disappearing. And similarly, the cloud cover also affects the downward long wave radiation flux. So this also is another reason. So here there is a comparison study. One is the overcast and another one is the partly cloudy sky. So based on that, when we measure, if it is a overcast sky, then the effort of cloud fraction is more, whereas if it is partly cloudy, it is less. So in other words, what we can say is, when we do the comparison of cloud sky downward long wave radiation algorithms using synthetic data, ground-based data and the satellite data. So this leads to the, from this if you see there are bigger error bars are there. So what do you mean by this bigger error bars? The error bars actually means there are lots of poor performance of the algorithms under cloudy conditions. So this is the, so if you look at the partly cloudy sky and the overcast one, and if we measure the cloud-based height, the error bars are extremely high here. The higher error bars in this graph indicates that there is a poor performance of algorithms that is used under cloudy conditions.